Hello and welcome to Software Architecture course. Today we are going to talk about a few more architecture patterns. So this pattern is basically a part of distributed systems, and in this particular pattern we are going to talk about how distributed systems are built and different quality attributes are actually addressed. So under the distributed systems, the most common pattern is called the broker pattern. We are going to study broker pattern today. So by now, in fact, I'm sure you have dealt with distributed systems somewhere. You are working on any web-based systems. If you have built any web-based systems, or if you have used any web-based systems, in both these cases you have encountered with a distributed system where there are many components which are on different computers, often geographically distributed, and they all work together to accomplish a particular task. So the context here is that the complex environment typically comprises of distributed systems, and what that means is that the various parts of your system is actually distributed across different computing infrastructure. So why do you want to do that? Because you want to take advantage of the computing power of many CPUs, or maybe you want to take advantage of a cluster of low-cost systems. And primarily such a design of exploiting the power of many CPUs or power of a cluster is that this complex environment or the complex problem that you're dealing with need to be addressed, need to be handled in an efficient manner. Typically in such cases there are many users who are working, who would like to use the system, or maybe the system is processing really time consuming task. So in such cases, if these tasks are distributed across multiple machines, then the task can be implemented, executed faster. There could be another reason that a software may be available only on a specific computer. So there may be some regulatory requirement because of which the software must reside on a particular computer. You can't just take the software and then distribute it or co-locate it with your application. It must be in a specific computer, and you can't really install anything there. Then you have got no option but to have your system on a separate machine and interact with this software. Due to security reasons, so far I talked about primarily performance reasons, availability reasons, but there are other reasons. Due to security reasons, you may want to run different parts of your system into different computers. In fact, some of the computers might be highly secured. One good example is any web-based application where the database application servers, they're all in a very secured environment. Some services which are provided by business partners need to be used to accomplish certain tasks, and your system might require the services offered by various business partners. Example, you are building system in which you would like to allow, let's say, credit card based authentication. Now actual credit card based authentication is actually performed by maybe Visa or MasterCard kind of companies or other banks. So you would like to use their service to accomplish the task, and if these need to be realized in real time, then you need to access the service over the internet. So this also makes the whole system distributed. So obviously it's not that simple to build a distributed system. There are problems. Now what you need is that you need to build a complex software system as a collection of decoupled interoperating components. You don't want a monolith to implement this. What that means is that you require a greater flexibility in your design, much better maintainability as well as changeability. And this partitioning of the system into independent components of course makes the system easily scalable, but the problem here is that partitioning it into independent components is not that easy, specifically if you have a monolith design or a monolith system. So partitioning is definitely not easy. So this is a problem there. Another requirement is that it requires a flexible means of inter-process communication. What that means is the inter-process communication mechanism itself should be somewhat flexible and decoupled from the actual system. Now, why? Because if you have a monolith and if you have two components interacting with each other, and specifically if they're a part of the same process, then interaction is not a problem because you are making a function call, method call. These are all in memory, in process communication happening. But the moment you basically distribute them, then it becomes an inter-process communication, and someone has to take care of this communication mechanism. And because this communication handling itself is a task that should not be given to the participating components. Again, if you have a monolith having two functions which are interacting with each other, f1 and f2, f1 is interacting with f2, if we just split them into two different boxes, in one box there is f1, another box there is f2, there has to be some component which is going to take care of interaction between f1 and f2, which was not there when f1 and f2 were together. Now, if these participating components, meaning if f1 and f2, they also handle communication, then the problem is that the design becomes quite complex and the system basically would start depending on the communication mechanism used. Client need to know where the server is, f1 need to know where f2 is, f2 need to know where f1 is, and so on. So those things are not really flexible. What are the other additional constraints or requirement? It should be possible to distribute the components during deployment time. Very important. What that means is that the application that you have built and which are going to be distributed, while the ideal expectation is that the application should be completely unaware of the fact that whether the service is co-located or remote, whether it is in the same machine or a remote machine, application development should be completely unaware of that. So if that's the case, then who should know whether the server is remote or in the same machine? That must be there while designing such a system. Someone must know. Then another requirement is to exchange, add or remove components at runtime. Therefore, one must not really depend on system specific details to guarantee portability, because these are all runtime requirement. I should be able to add or remove components at runtime and it should work. Therefore, while designing the system, you must not really assume certain infrastructure features or should not really depend on system specific details so to guarantee the portability or even interoperability. In other words, the architecture should be such that these system specific details like communication, distribution, portability and so on should be completely hidden from the actual functionality. So the system designers who are responsible for implementing the functionality should be completely unaware of these communication issues or interaction issues. Therefore, a broker pattern was proposed to address these concerns. This is a pretty old concept and it's still being used today quite heavily. Idea is that one needs to introduce something called a broker. So this broker component is introduced, and this broker component is introduced to achieve better decoupling of clients and servers. What happens is that the servers, one or more servers, typically register themselves with the broker and announce that their services are available. So announce it obviously to the clients, and how? It is through some kind of an interface, and client basically accesses this functionality of the server by sending requests to the server obviously, but via the broker, not directly. So the purpose of the broker is that it helps in locating the appropriate server, and it can also forward a request to that particular server. Well, I said that the clients access the functionality of a server and send requests via the broker. Sometimes client can even bypass the broker and make a request to the server directly, but that bypassing can happen provided client basically gets some information about the server via the broker. Only then it is possible. So in any case, client server interaction needs to happen through broker. You cannot just bypass it. So broker is responsible for locating the server and forwarding the request and also transferring the result. There is another solution. So in fact, in the broker pattern, because the broker helps in locating the server as well as transferring the data, and takes care, obviously that means it takes care of the communication responsibilities. It actually reduces the development complexity. So the broker pattern that we know today, the most popular was called CORBA, from which this today .NET, J2EE, all these platforms have emerged. The main idea was, the main pattern was implemented in this framework called CORBA. Now this broker pattern, as I said, it basically reduces the development complexity. How? Because it introduces the object model. So what that means is, if you are writing a distributed system, you feel that as if you are writing an object-oriented design. You are following an object-oriented design, normal object-oriented design. So it introduces an object model in which the distributed services are basically objects. So broker system basically gives a technique to integrate two core technologies. One is object-oriented design as well as distribution of the processing. So here what's happening is that the object-oriented designs, which were traditionally meant for single applications, now they suddenly become available to distributed applications. Now this can basically, so this distributed application can run on heterogeneous machine, and it can be written in different programming languages. That's a very important feature of CORBA, that one can write in different programming languages, and CORBA framework can understand this feature. This was quite useful when in early days people used CORBA based systems to enable mainframe systems to distributed platforms. This was one of the ways to do it. So the broker pattern, let's look at the structure, meaning what are the components there. So participating components for broker pattern are clients, servers, broker, bridges, client side proxy, and server side proxy. Let us look at what these components are. At a high level, the class diagram would look like this. So there is something called a service interface, and there is a broker. Now on the left hand side there is a client, and on the right hand side there is a server. So this service interface is this so-called announcement that the server makes, that here is the set of functionalities that I am going to provide. Now this service interface is obviously known to the client, because only through this the client knows what are the features that are available. If you look at this UML diagram, here this is an interface, and the actual server which implements this functionality realize this interface, meaning implements this interface. Then there is something called a server proxy, which also implements this interface. There is something called a client proxy, which also implements this interface, and there is an actual client. So there is an actual client, there is an actual server, and there are two proxies, and there is a broker. The broker, the job of the broker is to basically look at the server, look at the client, register services, and so on. So this is basically a necessary abstraction that makes a distribution possible through this contract, which is the service interface. So this contract says what are the features that the server is going to provide. It does not really expose the implementation, obviously, because it is an interface, and this makes it possible for someone to replace one server with another as long as the second server also implements the same interface. Another important part is that this whole class diagram can be distributed across three machines. The client can be in one machine, the server can be in another machine, and the broker can be in the third machine. So this is an important thing, that this is how one could partition this class diagram into three components, and they can be executed on three different machines. Let's look at the implementation of the broker pattern. So here the first step is to define an object model, or maybe one can use an existing one. Then decide which kind of component interoperability that the system must offer. Then identify the APIs the broker component provides for collaborating with client and service. Then implement a proxy object to hide implementation detail from the client and servers. Then while 3 and 4 are being implemented, in fact after step 3 one could actually start designing the broker component, and then one can actually also develop ideal compilers. Let's look at the first scenario, how this interaction can happen. In this particular scenario, in fact, we don't even have a broker. We will see an example of that. So that obviously means that somehow or someone should basically know where the server is. In this scenario, the client says that it wants to execute a particular function, perform function, and this client proxy, which actually has implemented the server interface, receives this call. Client proxy locates the actual server, so client proxy should know where the server is, and then it will marshal the data that the perform function is sending as an input. Then it sends a request to the server proxy. In fact, client proxy knows where the server proxy is. It sends a request to the server proxy. Then server proxy forwards the request to the actual server and sends the data. The unmarshalling actually happens at the server proxy level. Then the result is returned to server proxy. The result is marshaled, and then it is sent back to the client proxy. Client proxy does unmarshalling and sends the result back to the client. Therefore, this client proxy perform function that's implemented by client proxy actually does not have the business logic at all. But client thinks that it is actually making a call to the server as if it's a local call. So this call has got no impact per se with the server. Here it is all fine, only thing is that this servers cannot be relocated at runtime. Then this will not work. Broker can be used as a service locator, where the broker itself is residing at a particular place, a well-known place, and then it exposes that location to the client. That's a known place. Then broker takes the responsibility of locating the actual server. It is so the client need not know where the server is. Broker also implements a repository to add or remove different server components at runtime. That's important. Then once the server is located, then the client and server can talk directly. That's one approach. The broker is just serving as a service locator. It helps the client to get the server location, and then it let the client talk to server directly. This is how it works. Client calls perform function. It is a client proxy who need to know where the broker is. So client proxy calls the locate server method, and remember that we said these servers needs to register. So even before the whole application has started, the server has already registered itself with the broker. So broker knows that there is a server. Once this request comes, it sends the information to the client proxy, and then client proxy directly calls the request, or the client proxy directly sends the request data plus the request call to the server proxy. Server proxy does unmarshalling as before. Then it knows where the server is. The server proxy knows where the server is. It actually performs this perform function, gets the result, marshals it, sends it back to the broker, and server proxy doesn't really care where the client is. Now broker again tells the server proxy that here is the client. Then server proxy sends the response directly to the client proxy. Client proxy unmarshals this response and then finally gives the result back to the client. So let us look at another approach where broker actually serves as an intermediary. So here what happens is that the broker needs to directly communicate, or the broker does not want that the client and server should directly communicate. In fact, there are certain situations where such a requirement is there, that client and server need not really communicate directly. It could be because of the security reasons. Basically what you want to do is that you want to host all your servers inside your company's private network behind the firewall. In that case, and you also want all the accesses to go through the broker because you want to make an audit. So in such a case, broker would forward all the requests and responses between the server and the client instead of any direct communication. Let us look at the sequence diagram in this scenario. Here, as usual, client makes a function call perform function, goes to client proxy. So the client proxy does a marshalling and sends a request to the broker. The server proxy has already registered earlier, So broker knows where the server proxy is. It locates the server, forwards the request, server proxy unmarshals the input data, then actually calls this perform function. Server responds back then with a result. That result is marshaled again, and this marshaled result is sent to the broker, send response method. Then broker takes the responsibility of locating the client and then forwards the response. Client proxy, once it gets the response and of course the result along with it, it unmarshals it and then returns it back to the client. So let us look at a few known uses of this broker pattern. As I said earlier, one of the most popular and pioneering implementation is called CORBA. So CORBA is the oldest among all the middleware technologies that are used today in IT world. So CORBA stands for Common Object Request Broker Architecture. It is defined by its interface, their semantics, the protocols used for communication, and that protocol is called IIOP or Internet Inter-Orb Protocol, and CORBA supports the basic broker pattern. CORBA supports something called a dynamic invocation interface on the client side, and what DII does is that using this the client can discover what are the functionalities that the server is providing at runtime. That's very important, that it is not at a compile time but at runtime. Using the dynamic invocation interface feature, client can actually get what are the methods or the functionalities provided by the server, and then it can make a call. Now I use a term called IDL. IDL is basically a specification language to describe this service interface in which the server must write what are the services it is going to implement. This IDL is actually compiled, and this compiler is provided by CORBA. Not CORBA, CORBA is nothing but specification, but the products which have adhered to CORBA standards. So those products would provide IDL compiler, and that IDL compiler, what it does, it basically creates a proxy, client proxy, and also it creates a server proxy. Now client proxy is called client stub and server proxy is called the skeleton. There are various ORB extensions. CORBA actually supports client-side asynchrony via standardized interface, and what that means is that at the client side the client can make an asynchronous call. At the server side, asynchrony is supported only in a proprietary manner. There is no specification. However, the products implement it on their own way. Another usage is called RMI. So Java remote method invocation is basically based on transparent broker variant pattern, where actually there is no broker. It is the very first case that we had shown. Client and server talk direct. So client side proxy, also called stub, and the server side invoker, which is called skeleton, they have to be created and manually by an additional compilation step. So there is a compiler called RMIC that generates this stub and skeleton. In contrast to CORBA, in fact there is no service interface. It is all Java, so Java interfaces serve as IDL. So RMI is limited to the usage of Java only. However, CORBA is more generic. It can support C++, and as I said earlier, one of the major use case was to enable the legacy mainframe applications. However, RMI is only for Java. It is there to establish interoperability. Now, in order to do that, this RMI protocol needs to be there on top of IIOP. So it's a kind of a heavy duty protocol. IIOP itself is heavy duty, but on top of that, RMI is there to ensure that two Java remote components can talk to each other. RMI does not support any out of the box asynchronous call. You have to implement it. Now there is a central naming service called RMI registry, in which the servers can register and client can query. .NET is also similar pattern, broker pattern. So Microsoft .NET remoting platform essentially implements a transparent broker pattern like RMI. Here this .NET platform itself supports a mechanism called reflection to acquire different type information. The client proxy is created automatically at runtime behind the scene, unlike Java where you have to create using a compilation step. Here it is created behind the scene automatically. Application developer doesn't even know that this is created. So this eliminates additional step. In fact, no separate source code generator or compilation step is required in RMIC. In CORBA, everywhere it has this additional step. This essentially the stub and skeletons are nothing but source code generator. So the source code generator inside this ideal compiler would generate a fully compilable C code. In this case, it is not required in this case of .NET. The interface description for the client proxy can be provided again by a specific language feature called MSIL code or by WSDL description. Now, client proxy is responsible for, as usual, creating the invocation request, but it is not in charge of any communication related aspects there. Now, the remote communication functionality of .NET remoting is actually encapsulated within the framework. It consists of marshals or marshallers, so-called formatters. It's actually called formatters in the .NET language, and there are transport channels which basically abstract out from the underlying transport layer. So these transport channels are a high level abstraction over the traditional transport layer. It is quite flexible. It allows custom extensions to fulfill different quality of service requirements. In fact, unlike RMI, it supports client-side asynchrony. It also provides lifecycle management for various servers. However, there is no central naming system like Java RMI. Client have to know the object reference of the server in advance. However, there are different strategies that exist to avoid this hard coding. These are very specific to .NET. In fact, I would say that these different strategies that exist to avoid the hard coding are basically idioms. They are not patterns. So the benefits are obviously location independence. Client do not have to care about where the object is located. It can just use this remote object feature. In fact, through the remote object, it can communicate. It really doesn't have to hard code the IP address of the server. Here the assumption is obviously you are not using a transparent broker. Type system transparency is a very important thing, that because it is supposed to integrate different heterogeneous objects written in different languages, so therefore each language has its own type system. Now IDL basically offers a unified type system. Well, it is not really a problem in case of Java or .NET because they are only focused on Java or C#. In .NET, to an extent, it allows other languages, objects built on other languages to also come and join. Therefore, type system transparency should be there in .NET, but it is certainly not required for Java RMI. Another benefit is isolation. The communication related logic is completely separated from the business logic. Separation of concern, this communication, marshalling, etc. are really not linked with the actual functional module. The resource management is actually done by the broker. Now, in terms of connection pooling, buffer, network related issues, these are all handled by the broker. Therefore, the clients are not really bothered about this. It is definitely portable. The code is definitely portable. As long as you have appropriate broker for the particular infrastructure, your code will work. There are liabilities as well. Error handling is definitely a problem, just like the Blackboard architecture. Clients have to cope up with the inherent unreliability of this many things like network communication, the server failure. The client has to deal with this. There is obviously an overhead. One overhead is that the developers can typically forget about the location of the objects, which can actually cause an overhead if these expenses of remote communication are not really considered. There are performance issues because it is slow. It is certainly much slower compared to if it was there in the main memory, non-distributed, primarily a tightly coupled co-located system. In that case, performance would have been much better. If specifically performance would have been better if it is not implemented the way this broker pattern is suggesting. Here obviously there is a overhead of the broker itself. The fault tolerance certainly goes down because of the broker being a single point of failure unless certain availability patterns are applied to make sure that the broker is also highly available. Other than if that's not there, then it becomes more vulnerable to faults. Testing and debugging is definitely a problem in this broker pattern. So that's it for the broker pattern. We'll continue with few more architecture patterns in the subsequent lectures. Thank you.